Welcome to Module 5, Part 3. Till now, we have seen the first order low pass filter, second order low pass filter, and its design. Next, we'll see the first order high pass filter. So, this is the diagram of the first order high pass Butterworth filter. The only difference between the low pass filter and high pass filter is the capacitor and the resistor over here. So this is interchanged. For the low pass filter you have a resistor here and a capacitor here. Now for this high pass filter we have a capacitor and a resistor. So it will pass the high frequency signal to this non-inverting terminal of the op amp. Low frequency signals are blocked by this capacitor. Resistor R1 and RF determine the gain of the op amp. Since the input is connected to the non-inverting terminal, the gain AF over here is determined by R1 and RF, which is given as 1 plus RF by R1. The output voltage V0 is gain times, that is AF times this particular voltage at this point. So this is calculated by the voltage divider rule, which is Vin into R divided by minus JXC plus R. So this is minus JXC. So this point we can take it as V1 is Vin into R divided by minus JXC plus R, and RL is the load resistance over here. Moving on to the frequency response. Since this is a high pass filter, it will pass the high frequency signal and the low frequency signals are blocked or attenuated. Any frequency less than FL, which is low cutoff frequency, any frequency below this FL is blocked, and that forms the stop band. Frequency beyond this FL is passed, which forms the pass band. The role of rate, as we have already seen for the first order filter, is 20 dB per decade. For every 10 times rise in the frequency, the gain falls at the rate of 20 dB. For higher order filters, this comes closer to the ideal. Moving on to the equation, output voltage equation, as I have already told, V0 is gain. This part is the gain of the non-inverting amplifier into the input voltage, which is given as Vin into R divided by minus JXC plus R. So we already know that minus JXC is equal to 1 upon J 2 pi FC. So we know this particular equation. Minus JXC equals to 1 upon j 2 pi fc. Substituting this in the equation where we have minus jxc, we get this particular output equation. The gain into V in into j2 pi fcr divided by 1 plus j2 pi r fc. So V naught by V in, bring this V in down, and this is AF, and this becomes F by FL. Since we know that FL equals to 1 upon 2 pi RC. So 2 pi RC becomes 1 by FL. So this is J into F divided by FL divided by 1 plus J F divided by FL. So here AF 1 plus RF by R1 is nothing but the passband gain of the filter. F is the input frequency here. FL is the low cutoff frequency, which is 1 plus 2 pi RC. We already know that. So the gain magnitude equation now becomes AF into F by FL divided by square root of 1 plus F by FL the whole square. So with the gain magnitude equation, we check the operation of the filter. So with this gain magnitude equation, we verify the high pass filter. So we already know the equation of V naught by V in. So it is AF into F by FL divided by F by FL plus 1, this whole square into the square root. The square root. So at low frequency, what happens when F is less than FL? So this becomes large quantity. So there will be some value over here. This into F by FL divided by some quantity. So it will be less than AF. We know the graph, the frequency response. So this is the frequency response. We have the cutoff frequency FL at this point. This is 0.707 AF. This is the constant AF. So when F is less than FH, this is the response of low pass filter. It is less than AF for high pass. So when F is less than FH, the gain V naught by V in is less than AF. At F is equal to FH at this point, the gain of the filter is 0.707 AF, and when F is greater than FL, so F greater than FL, F equals to FL, and when F less than FL, so the gain V0 by Vin is equal to AF. We can substitute that F is greater than FL, so FL will be a small quantity. Any number divided by small quantity can be negligible, so this part can be negligible, and then square root of 1 will be 1. This part will be 1, and F greater than FL, so FL is negligible, so the entire quantity can be negligible, so AF divided by 1 is AF. So any frequency beyond this FL over here will be AF. Frequency less than FL will be less than AF. Frequency equals to FL will be 0.707 AF. So with this gain magnitude equation, the operation of the high pass filter is verified. Next we'll move on to the filter design. First we have to choose the cutoff frequency, that is FL, which will be given visually. Then we have to choose the capacitor C, which is should be less than 1 microfarad. Generally we select 0.01 microfarad. Then we have to calculate the R using this equation, 1 by 2 pi Fc. Then we have to calculate the resistance R1 and RF using this gain equation, 1 plus RF by R1. We select R1 to be 10k ohm, and based on this we can calculate RF. So you can take an assignment problem 3 to design a first order high pass filter at a cutoff frequency of 5 kHz. FL is given 5 kHz, FL is given, then AF is given 2. First you have to select the capacitor C, 0.01 microfarad. Then you have to calculate R, 1 upon 2 pi Fc. F is given, C is chosen. Based on that you can calculate R. Then you have to select R1 as 10 k ohm, and based on R1 and AF you can calculate RF. So you have to draw the diagram of the first order high pass filter and put the values there for the components. Thank you.